Okay, good afternoon. Yeah, I'm Jacopo Cassandro from Politecnico di Milano, and together with Claudio Mirarchi, we developed this first research about an ongoing project that we started a couple of months ago regarding the topology-driven semantic integration of independent BIM models for renovation analysis. Let me first introduce about a little bit the broader research context, because our research is not simply about converting BIM model into RDF, but the main objective is to develop a processes that automatically transform a geometrical BIM model into semantic analysis ready representations, depending on the application we want to support. Starting from the same BIM model, now we can and different semantic views can be generated for application, such as for energy analysis, LCA, cost management, and facility management. And in specific for this paper, we addresses one specific challenge regarding the semantic integration between independent BIM models creating during a renovation projects. Renovation projects are typically characterized by multiple BIM models representing different project phases, such as the existing condition, and the proposed retrofit intervention. And since these models are often developed independently and stored in separate IFC files, they do not contain explicit semantic relationship between the corresponding building elements. As a consequence, performance-related information is fragmented, making automated analysis such as energy assessment much more difficult and often require manual model merging or then adjustment. Existing approaches generally assume that semantic relationship are already available or can be directly derived from a single BIM model, but however, this assumption does not hold in renovation projects where the model remain completely independent. And our research therefore investigate these three research questions on how can agency relation between independent BIM models be inferred from surface level geometric evidence, how can such relation be semantically created without model merging, and how can the resulting semantic model support performance-oriented data extraction in renovation scenario. To address these questions, we propose a geometry-driven and ontology-based workflow. As you can see here, we start from the input data, that is our independent IFC models. Then in parallel, we have a first part where we analyze the geometry of the independent models to detect physically meaningful contacts between the objects. Then both IFC models are translated into RDF reusing existing ontologies, building topology ontology and building element ontology. And finally, the detected agency are transformed into explicit semantic relation, enabling cross-model reasoning and automatic extraction of analysis-ready information. So the core part of the methodology is the geometry-driven topological analysis. Rather than simply detecting nearby objects, the goal is then to identify the physically meaningful contact interfaces between elements belonging to independent BIM models. And two surfaces are considered adjacent only if three geometric conditions are simultaneously satisfied, if they are coplanar, if they have opposite orientation, and then if they present sufficient overlap at the end. Together, this condition prevent false positive by excluding surfaces that are only geometrically close but do not represent a real physical contact. Once these conditions are satisfied, an overlap metric is computed to quantify the significance of the detected interface. And this is something that we can do automatically with a specific algorithm. Then in parallel, Both IFC models are independently translated into RDF reusing the both and the ontology. And rather than merging these models, we create semantic bridges between them, and each detected interface becomes at the end a bot interface instance, connecting the corresponding elements of the two different knowledge graph. This interface at the end explicit this connection between the elements while preserving also the model independence to each other. In this way, purely geometric evidence becomes machine interpretable semantic knowledge, and then that can later be queried and exploited more in detail. The case study and the validation of this proposed methodology use a really simplified renovation scenario. The existing model represents at the end a wall composed of multiple layers, an existing wall composed of multiple layers with an opening window, with a window at the end. The retrofit model contains only the newly added insulation system. And this is a really simple at the end case study, but was designed as a simplified yet representative scenario because it reflects at the end a common building envelope renovation scenario that we have also in our project, in the case study of our project. The geometry-driven analysis successfully detects all the relevant agency automatically, and in particular, one existing wall, as you can see on the left part, matched at the end correctly with 4 separate insulation panels surrounding the window opening, and all detected interfaces achieved an overlap ratio higher than 94%. There's also some percentage that is missing, but it's based on probably some misalignment between the models. Once the geometric matching is completed, as I told you before, now the detected interfaces are automatically converted into semantic relation, and each interfaces are represented as a both interface instances. This creates at the end an explicit semantic bridge between the two original independent IFC model, allowing at the end an object-to-object relationship to be queried and reasoned upon without modifying the original IFC model. After that, once semantic links are available, then we can query the knowledge graph and extract all the information that we need, in this case, thermal transmittance or any other information that we need for the existing and retrofit elements that are now connected in just a systems, such as a building envelope or something like that. So to conclude, we presented a geometry-driven and ontology-based methodology for semantically integration independent BIM models. The proposed workflow reconstructs envelope system without merging the original AFC file, without any manual intervention, and enable also machine interpretable relationship between the existing and retrofit elements. And we create this also temporary model regarding this condition, this specific condition. Although the results are promising, but some limitations remain. The quality also of the analysis strongly depends on the quality of the input data of the original IFC geometry. And moreover, the current validation has been performed only on a simplified case study. And for this reason, future work will focus on larger and more complex renovation scenario, as well as on evaluating computational performance and scalability for real-world buildings. Thank you for your attention.